class we have discussed about the order and disorder transitions, order-disorder transitions. So now I will talk about a way to characterize the order and disorder in an experimental setting, and as we have already pointed out in the last lecture, it is known as scattering. So we will briefly discuss the scattering theory, what is known as the Bragg's law, that is one of the simplest descriptions of scattering, and then I will not derive the complete expressions for the actual result from the setup, but I will discuss at a qualitative level what does that mean and how does that relate to the pair distribution function that we have discussed earlier. Okay. So let us talk about scattering. So the fundamental basis of scattering experiment is the fact that the light, and when I say light, it can be any type of light like UV light, visible light, it can even refer to an X-ray or some other kind of a light source. But all these kind of lights will have some particle nature and some wave nature. So essentially, just to remind you something about the waves, waves do possess something known as a wavelength that characterizes some sort of a length scale of the fluctuations of the wave, and that is related to something known as a wave number, that is called k. So this is for a one dimensional sort of a wave. We can generalize to a 3 dimension. So then we have, instead of a lambda, we will have lambda x, lambda y, lambda z, and essentially we will also have a wave vector in place of wave number. So this is the earlier one is called wave number, but a general case will have a wave vector k. And essentially what we do in any scattering experiment is, let us say we have a sample. Let me highlight the sample by some sort of a color to characterize, there is where the light is going, and let us say we send a light with certain wave vector. That light is then diffracted or scattered, and we get a new wave vector in return, and this tells me the magnitude of the obstacle the sample presents to the light source. Okay. So the game is between a wave interacting with a particle obstacle. Depending on how big the obstacle is or how rigid the obstacle is, it will change the amount of scattering that we can receive, and the amount of scattering essentially is given like something of the order of k prime minus k. I can reproduce a k here, and then using the triangle rule this particular vector become my k prime minus k, actually opposite of that. So you can see if I add k with k prime minus k, I get the vector k prime. So, that is the essential idea of scattering. And now we will see like how does the scattering give you a different result in the case of a solid, liquid and gas. So, a solid, as I said, has a repeating pattern of or repeating arrangement of molecules. So, in a very simple kind of thinking or a simple kind of an experiment, we can approximate the crystal nature or the solid nature as a set of infinite planes that we have in the solid. So, let us say if I am looking at a FCC crystal, I can see a series of 100 or 111 planes depending on how I am cutting across the solid, and each of these planes then in general will have some kind of a scattering pattern, and this is what we will discuss, and this is what becomes the basis of what is known as the Bragg's law. We will talk about the Bragg's law, and the assumption is we are considering the solid to be a set of infinite planes, okay, because if you think of a bulk solid, it will indeed have these different planes coming in, and then a light source comes in, and it is scattered by each of these planes. So, we have a k here and k prime in return. Now, in practice many things are happening when the light source comes and hit this infinite set of parallel planes, but essentially what matters is how many of them have a constructive interference, and we only look at the final result after the constructive interference. Destructive interferences will basically cancel out, and I am not really going in details here, but the basic idea is that we are looking at the superposition of all the constructive interferences. So, then if I look at say two adjacent planes, let us say I and I plus 1, and if I look at the scatter through them, then if I look at these two, they differ in the length of the path by these small. This is the length difference that we see between the two waves and their scatter between two adjacent planes, okay. And this is what I will refer to as the difference in the path length. So, this may be coming at an angle theta, and then it of course leaves. So, of course, this light also goes to other planes. So, the net scatter can be something like 2 theta, and this distance can be d, that is the distance between two planes. So, we have a d there. So, we have another theta in between. So, essentially this particular quantity become d sin theta here and d sin theta there. So, difference in path length becomes 2d of sin theta, and this is equal to n times lambda, where n is an integer and lambda is the wavelength of the fluctuations that we have in the system, in the light source. Okay, so I am not really completely deriving it, but essentially the idea is that we have a series of planes and the scatter through each of them will give rise to differences in path length, but those differences will be integer multiples of the lambda of the light source. So, now what this means is I can get, by looking at simply the lambda by 2 sin theta, this is the distance between two planes. Okay. So, and that basically means that if I do not know the d to begin with, and if I know the wavelength of light, if I know the scattering angle, this I can get from experiment, I can get the periodicity of the solid by means of doing this scattering experiment. Okay. So, note that when I say a d here, that can be the difference between any two planes. That is why I have used n here. This d is between the two adjacent planes. So, let me use a different word here, let us say 2d sin theta, capital D, and this small d is between the two planes, just to avoid any confusion. Okay. So, this is the basic idea of scattering experiment, that I can do a scatter, I can know the wavelength of light to start with, and I can measure the scattering angle theta, and then I can get the periodicity of the surface. But then if I have other kinds of solid arrangements, this particular approximation we have made of infinite set of parallel planes will not work, but the basic essence that we can get the periodicity, or we can get information about the order through the measuring of scattering angle and through measuring of the wavelength of the light source, continue to work. What it also means is, if I want to look at structures with a certain periodicity, I have to choose the light source of a certain wavelength. For example, if this lambda value is very small, I can look at smaller values of d. On the other hand, if lambda values are large, I can only get larger values of d. So, depending on the light source, the resolution into which we can go will change, and that is the reason why we have many kinds of scattering experiments available. We can do neutron scattering, we can do X-ray scattering, we can do of course visible light scattering, ultraviolet scattering, and so on. Since they possess different wavelength, they essentially are applicable to different length scales that we are interested in. Okay. So, with this background and without actually deriving the expressions, I will present what does the scattering experiment gives you, and then we relate back to the theoretical description of the pair distribution function that we have discussed earlier. So, an scattering experiment essentially gives you what is known as a structure function I of q, where q is defined as k minus k prime, and this is x alpha minus x alpha prime, where alpha and alpha prime are indices over all particles in the system, which may refer to molecules or segments depending on the length scales the light source can resolve. Okay. So now you can see that IQ is extensive, since we are simply adding up over all the possible indices. If the number of particles increase, we will have a higher values of IQ. So we want to have a measure that is independent of the number of particles. Let us call the number of particles to be n. So we can define an intensive measure that is known as structure factor and in literature there are two ways it is defined. In one way we divide by the number of particles, in other way we divide by the volume of the system. In both the cases, since the volume also scales like the number of particles, we do get an intensive quantity. So one way is and other way is if you are looking at any particular literature on the structure factor or scattering, you should be careful how exactly they are normalizing it. Is it by n or is it by v? But both of them are anyway related. So S tilde is S multiplied by n by v. So we will now show that the structure factor is basically a Fourier transform of what is known as a number density correlation function, that in turn is related to the pair distribution function, as we will discuss. So before this I will define the number density which is similar to the concentration that we have derived when we are doing the virial expansion. Essentially we are interested in the numbers per unit volume. So we can add up delta functions for every particles at a particular position x, and since delta function has a unit of 1 by volume, we do get a number density. So essentially it is so we sum over all the particles for a particular position x. So if a particle is at x, I will add 1. If a particle is not at x, I will add 0, and after summing it over, we divide by the volume and we get the number density at a particular location x. So if I take an ensemble average of the number density, we should get the number by volume only for a homogeneous system. Like a liquid. In a liquid, the molecules can essentially take up any position. Of course, in a particular conformation, the molecules are only at particular position, but if I take an ensemble average, what we will find is that the number density gives me a number that is simply n by v, that is the average density of the system numbers per unit volume. This is not true if we have a solid, because in a solid there are only particular positions in space where the molecules can be, they cannot be anywhere. So, if I take an ensemble average, still we will see there are vacancies in between where the number density will essentially remain 0. Okay. So, only for homogeneous systems we can make this particular approximation. For a solid, this is a periodic function, however, and why is that? Because just to recall how a solid look like, so if I find a number density here, 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 here at certain distances, we should get the same value. Similarly, if I find the number densities say here, 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 again we always see a vacancy. That means that if I do an ensemble average, I should get a periodic function. It will repeat after certain values of x. Okay. So, now I can define a number density correlation function which is written as CNN x1 x2 and is equal to ensemble average of n x1 n x2. That means, what is the probability effectively that if a particle is at x1, another particle will be at x2, although we will normalize this probability later, but this is what it is. So, we look at the case where one particle is at x1 and we want to know what is the probability where another particle is at x2. So, now we will have two delta functions, one for x1, another for x2. Okay. So, now if I Fourier transform this particular correlation function, let us see what do we get. So, when we do a Fourier transform, essentially we do this So, this is what I have added to do a Fourier transform. You can see it is an extension of a Fourier transform in one dimension if you are not used to a Fourier transform in 3 dimensions. So, now I can move this thing inside But before this, let us use the expression that I have just discussed. So, now I will move this in, and you know that if I integrate a delta function over the entire volume and I multiply the delta function with a function, I can simply substitute the x1 for alpha here. So, only case where the delta function will have a finite value is when x1 is equal to x alpha. So, we can remove the integration and simply put x1 equal to x alpha. So, the first term will be similarly for the second term, if I integrate over dx2, it will only be finite for x2 equal to x alpha prime. But now we have a plus sign, and both of them are summed over the respective indices alpha and alpha prime. So, now you can see both I am summing over all the particles. So, actually I can use the same index for the next part as well, it makes no difference. So, I can write it as since the second one is also a sum, and which I can write as where this is a Fourier transform of nx. This is also a Fourier transform, but just with a minus of q. Okay. So, essentially what we can conclude from here is if I Fourier transform the number density correlation function, what essentially I do get is my structure function, because this is what we did get after I did the Fourier transformation. Okay. So, this gives me I of q. So, now we have a perfect relation. We can theoretically get the number density correlation function, or through by a simulation we can get that quantity, and I will Fourier transform that, and I will get the structure function that I can then get by experiment, and then we have one way to compare the theory with experiments. There is a catch here, however. The catch is that the inverse is not possible. Let us say you do an experiment and you do get IQ, I cannot back calculate the number density correlation function, because the inverse Fourier transform turns out to be difficult than compared to the direct Fourier transform. So, we can do for certain cases, particularly if we have like a homogeneous isotropic fluid. In that case, inverse Fourier transform can be possible, but in general we can easily get I of q, the structure function, by Fourier transforming our number density correlation function, but we cannot do the experimental IQ inverse Fourier transform and get back the theoretical value, and this remains a challenge. It is called the inverse problem in mathematics. Okay, so I will stop with this. In next class we will discuss the what is known as the pair distribution function, which will essentially be a function of this number density correlation function, and from there we will go to the discussion of the particle simulations, especially the Monte Carlo simulations of polymers, and then we will see how we can use those simulations to get the number density correlation function or the pair distribution function that we discuss, so that we can have a systematic way of looking at the structure of polymer systems. Thank you.